Looking at this image, you are seeing only a tiny fraction of Omega Centauri. Packed tightly with 10 million stars, this dense 12-billion-year-old formation is actually the stripped core of an ancient galaxy that was absorbed into our Milky Way. Given its massive stellar population and extreme age, the laws of stellar evolution dictate exactly what should be left behind inside it. When the most massive stars burned through their nuclear fuel billions of years ago, they collapsed into black holes. Based on the math, there should be around 10,000 of these stellar mass black holes sinking toward the center of the cluster, but finding them has been maddeningly difficult. Astronomers scanned the cluster for the X-ray flares of feeding black holes, and they measured the speeds of stars, hoping to catch the gravitational tug of hidden companions. Both methods turned up absolutely nothing. The math guaranteed a massive population of dead stars, yet they remained invisible. 10,000 black holes were successfully hiding perfectly in plain sight, deep inside the most crowded neighborhood in the galaxy. To catch something hiding this well, researchers had to switch tactics and rely on astrometry. Instead of looking for radiation or broad speed shifts, astrometry involves measuring the microscopic physical movements of a star's position against the background of space over years or even decades. A team looked back through 2 decades of archival images taken by the Hubble Space Telescope. They cross-referenced that historical baseline with ultra-precise, modern infrared measurements from the James Webb Space Telescope. Out of millions of data points, they successfully tracked one normal, main-sequence star exhibiting a tiny, systematic wobble. It wasn't moving in a straight line. It was being pulled off course by the immense gravity of a completely dark companion. They had caught their first hidden black hole, officially naming it Omega Cat BH2. But the moment they calculated the properties of this invisible object, the data immediately contradicted our basic understanding of how stars die. By measuring the exact arc of the visible star's wobble, the team weighed the dark object. It tipped the scales at exactly 4.46 times the mass of our Sun. This chart shows the dividing line between dead stars. On the left side, a dense neutron star maxes out at roughly 2.5 solar masses before collapsing. On the right, typical black holes usually start around 5 solar masses. At 4.46, Omega Centauri H2 sits squarely in a forbidden zone known as the mass gap. Its strange weight gets even more confusing when you look at its environment. Omega Centauri is extremely metal-poor, meaning its stars contain very few elements heavier than helium. In standard stellar models, metal-rich stars produce fierce solar winds that blow their outer layers into space, shedding weight as they age. But metal-poor stars don't have those strong winds. They hold on to their mass.
Because they retain all that extra material, metal-poor stars are mathematically supposed to collapse into massive black holes, weighing anywhere from 10 to 20 solar masses, or even more. Yet here is a 4.46 solar mass black hole, sitting right where it mathematically shouldn't exist. To produce a black hole this light in an environment this metal-poor, our accepted models of stellar death have to be missing a crucial mechanism. The object's weight is only the first anomaly. By tracing the star's path over the 20-year dataset, astronomers realized it takes exactly 94 years to complete a single orbit around the black hole. Most known black hole binaries orbit each other in a matter of days or hours. At 94 years, the physical distance separating these two objects is massive, roughly the distance from our Sun to Neptune, making it the longest orbiting black hole binary ever discovered in a star cluster. That vast separation tells us a lot about their history. If a star and a black hole are born together as twins, they have to orbit extremely close to one another to survive the explosive supernova that creates the black hole in the first place. At 94 years apart, the initial supernova would have easily broken their gravitational bond. This means they didn't start out together. Instead, this system dynamically formed. The black hole drifted through the incredibly crowded core of Omega Centauri until it happened to cross paths with a wandering yellow dwarf star, capturing it in a wide, delicate gravitational embrace. To account for Omega Cat BH2, physicists now have to reverse engineer their stellar evolution models. They need to find a new pathway that allows a massive metal-poor star to shed a huge amount of its mass before dying, leaving behind a lightweight remnant.
Getting that math right matters far beyond Omega Centauri. Extremely dense globular clusters act like giant cosmic factories, constantly forcing solitary black holes and stars into these dynamically formed binaries. Eventually, as these paired objects lose energy and spiral inward, they violently merge. Those distant, cataclysmic collisions generate the gravitational waves that wash over Earth and trigger our modern observatories. We rely on our models of stellar evolution to decipher the origins of those waves. If our baseline assumptions about how black holes form and capture partners are flawed, our map of the gravitational universe is incomplete. But this specific partnership won't last very long. Because of its fragile, wide orbit, gravitational encounters with other passing stars will violently tear the visible star away from the black hole in less than 1 billion years. Fortunately, we now know exactly how to look for them. With the upcoming launch of the Nancy Grace Roman Space Telescope, astronomers have a proven astrometric blueprint to scan the crowded galactic bulge with even greater precision.